today, the conclusion, comparing how we used to program graphics on the Apple II Plus with AppleSoft Basic and on the TRS-80 Color Computer with Extended Color Basic. The previous video introduced the two computer lines and explored how they supported low-resolution and high-resolution modes, plotting points, lines, and other geometrical shapes, and some of the very weird and unexpected results you could run into. We also analyzed what BASIC was trying to do in order to understand these strange quirks. In this video, we move forward with some of the more advanced techniques in BASIC graphics, such as Flipbook-style animation with off-screen buffers, drawing arbitrary shapes, and moving them across the screen. And yes, we will go into full detail on AppleSoft's super normal and straightforward shape tables, a very natural way to draw shapes from BASIC which aren't unreasonable at all. When I was in middle school, I had access to their Apple IIs, and I used them to work on a game for a contest. A game which I still have to this day. And thanks to Retro Floppy, I got this converted into a virtual disk file. But just in case that floppy didn't work, I also printed it out. The Battle of the Jupiter Jerks. And at the end, you can see there's something that doesn't look like BASIC at all. And I was thinking about that, and I was trying to remember the time when I was working on this, and I remember there was some weird stuff I had to learn, and I don't remember how I learned it. I just knew that it was hard, it was difficult, it wasn't quite BASIC. It was shape tables. And when I saw those weird hex codes at the end, this inspired me to crack open the code, learn about it again, and then make these videos. Neither the Apple II Plus nor the CoCo have support for hardware sprites. So if you want to put a figure on the screen and move it around, it's on you. You got to write the code to do it, and the CPU is going to be busy running that code for you. So they each have their own ways of doing this in BASIC. By the end of the last video, we were at a 3-3 tie between the CoCo and the Apple II Plus. Let's see what happens when we explore some of the more advanced graphics capabilities of the two machines. The CoCo provides built-in support for page flip animation. So as an example, we're going to draw a whole bunch of Space Invaders on this screen. And it's going to take a bit of a while, so let's kind of skip ahead to the next phase. And next we're going to draw a bunch of Space Invaders that have moved slightly in the next screen. And again, it kind of takes a while to draw all of them, so let's just skip ahead to the next phase. And now that both pages have been completely drawn, we can instantaneously switch back and forth between those two pages. Kind of like if you had a Flipbook and you were going to draw different frames in it to make an animation, that's what's happening here. The key to getting this to work is the second number in the pmode command. In the previous video, I talked about both the pmode and the screen commands. This number picks the video mode. This number picks your color set. This number needs to be 1 to ensure you're on the graphics screen. And I kind of just avoided this number, but now we need to know. The CoCo divides up its screen memory into blocks of memory called pages. The video mode you choose determines how many pages are needed to fill a screen. In this video, we've been focusing on Mode 3 and Mode 4. They're the highest resolution modes, and they each require 4 pages. But the nice thing about the CoCo is that if you didn't need all that resolution, but you could use a little extra memory, you could pick some of these lower resolution modes and use less memory. Although they provide less detail than the Modes 3 and 4 screens, they're still higher resolution than what the CoCo calls its low resolution mode that we discussed in the previous video. This second number determines which page the CoCo is going to start writing to when you do some drawing on the screen. Typically, we've just been using 1, which means start at the very beginning of video memory. But since these screens use 4 pages of memory, we could also start on page 5. That begins a whole separate screen full of memory. So the way this demo works is we start writing to page 1, and in this for loop we just draw a whole bunch of invaders. We then switch over to starting at page 5 and draw the other screen full of Space Invaders. And now we can switch back and forth by simply picking the page we want to show and using the screen command to display it. The rest of this code is just the subroutines for actually drawing the Space Invaders themselves. It takes a while to run all that code, but we just run it at the beginning to fill up the screens, and then we can flip back and forth between the screens instantaneously. On the Apple, we can basically do the exact same thing. The way you do this on the Apple is simpler, but also less flexible. The P mode and the screen commands are combined into a single command at once. HGR says we're going to write to the first buffer and we're going to display the first buffer. So we turn on the first buffer and we draw our invaders. HGR2 moves us to the second buffer and displays the second buffer. And then we draw the second batch of invaders. But the other thing these commands do is clear the screen as well. So if we just use HGR and HGR2 to flip back and forth, we would erase all of the good work we did. So unfortunately, we have to resort to using magic pokes that will flip us back and forth between one screen and another without actually erasing them. As before, the rest of this code is simply drawing code to actually draw all the invaders. Both the CoCo and the Apple II give you nice Flipbook animation functionality, but the CoCo has dedicated basic keywords for this, whereas with the Apple II you have to use magic pokes. Plus, the CoCo can be more flexible. You can downgrade your resolution, and in exchange, you can use the saved memory to create more pages to do your animation with. The CoCo wins this round. Why do you never see two pixels beating each other up? Because it was cut due to graphics violence. And that was today's Pixel Perfect Pun, brought to you by Bing. Bing, America's favorite way to search for Google. The CoCo has built-in functionality to let you draw shapes using relative drawing commands. Until now, all of the drawing commands required that you specify the exact coordinates. But for this command, literally called draw, you can provide it with a string with a bunch of mini commands that direct a pen where to go. The CoCo remembers where the pen is, and then you can tell it draw to the right 2 pixels, draw down 2 pixels, draw up 7 pixels. You have the 4 horizontal and vertical directions, and the 4 diagonal directions you can use. There's also an absolute command you can use inside that tells it to go to a particular coordinate. You can also change the color midstream, the angle you're drawing at, and the scale. So can you guess what this string will draw? That's right, it's a cow! And since these instructions are all relative, I can reuse that string and change the scale using the S command, and change the angle by using the A command. So we can draw a tiny little cow a little bit bigger, all at different angles, getting bigger. Lots of cows. Cows everywhere. Until they fill up the screen and become unrecognizable. The Apple has similar functionality. The equivalent code draws the same cow here, and we can also change its scale and its angle until we have just too much cow. But the way the Apple does this is so different. The first few steps you'd go through are fairly similar to what you do on the CoCo. You would first want to design your shape, and then you'd need to draw a path that goes through the shape. This is the path that your pen will take. Now change that path to a series of vectors where you have arrows coming out of the dots. Sometimes you have a vector where you draw a dot, and sometimes you have a vector where you just move without drawing. Now go ahead and draw out all those vectors in order but on a single line. These are the commands that you're going to tell the Apple to draw in. Now arrange those vectors into bytes, with each byte being a group of 3, or maybe 2, or sometimes one section. We will call these sections A, B, and C, where A occupies the low 3 bits of a byte, B is the middle 3 bits of a byte, and C is the top 2 bits of a byte. Each section reserves the bottom 2 bits for the direction and the top bit to decide whether a pixel is drawn or if you're just making a blank move of the pen. Now you may be wondering how section C can properly represent a command with only 2 bits. Well, C can only represent a blank move, so the pen down bit is assumed to be 0. However, C cannot be 0, 0, which would normally be a blank move up. So if you're up to section C and need to do a blank move up, simply leave it 0, 0, but then encode a blank move up that's 0, 0, 0 in section A of the next byte. Next, use this handy table to convert your nibbles, which are 4 bits, and thus always straddle multiple sections, into hexadecimal digits. You now have the bytes of your shape in hexadecimal form, which we call your shape table, and they are ready to enter into the Apple monitor, but not so fast. It's time to generate a little metadata first. We need to create a shape table header that tells the Apple how many shape definitions we'll store and the offsets each shape definition reside at relative to the start of the header. And of course, we need to decide on a good address to store the shape table at. Now we can enter the Apple monitor and start typing our bytes. Don't make any mistakes. Almost done. We just need to tell the Apple the address we chose for our shape table. Go to well-known address 00E8 and enter our shape table's address there. You'll probably want to save this to tape or disk just in case something crashes or the power flickers. That was the actual advice from the AppleSoft basic manual. Believe it or not, I even left out a couple details. But for what I did for this video, I didn't follow the advice exactly. First, I did not use the Apple System Monitor to enter all of these bytes and then save them separately. Instead, the program that actually uses the shape table also pokes it into memory. I just used a bunch of data statements and a loop that would poke all of those bytes into memory. This kept everything self-contained in a single program. And secondly, there was no way I was going to come up with these numbers manually. It is way too error-prone. So I wrote a little bit of Java code, which would accept the draw string from the CoCo that I already came up with, and would convert each of those commands into the bytes by following all of the rules that you need to follow without me needing to worry about it. Even if I was only going to use this code once for a single shape definition, it was worth it rather than having to do everything myself. Once your shape table is complete, fortunately the rest of the code is pretty reasonable. The rot equals statement and the scale equals statement set the current rotation and scale that will be used when the shape gets drawn. Then you simply draw it using the draw command, which coincidentally is the same name as the command you use on the CoCo. But in this case, you follow it with the index of the shape and the location where you want the shape to be drawn. Now that we have our cow, let's get it to walk around. On the CoCo, you have a couple choices. The first choice is simply to use the draw command, but to change the starting point. If we loop and change the starting coordinates to be moving to the right of the screen, then there we go. A perfectly drawn cow walking around the screen. Obviously, we would need to erase the cow from the old location before drawing it in the new location. But basically, something like this would get the job done. But there's another way. The CoCo allows you to grab a rectangular portion of the screen and to store it in a special location in memory, so you can then put it back onto the screen wherever you like. It's kind of like a clipboard for graphics. The get command copies that rectangular portion of the screen into the clipboard, and put will paste it from the clipboard back onto the screen wherever you like. Of course, the CoCo does not really have a clipboard. So to tell BASIC where you want to store that portion of the screen, you have to create an array of the correct size. In the case of the cow, I declare an array CO using the height of the cow in pixels and the width of the cow in bytes. We can then draw the cow once and use the get command to store all of those bytes into our array CO. And now in a loop, we can put that rectangular region back onto the screen, going from x-coordinates 0 to 100. Since we grabbed an entire rectangle of space, we're including a bunch of the black pixels around the cow. So without doing any intentional erasing, it's looking a lot better. But of course, any pixels that are right on the edge are going to leave that streak. So we'd want to work a little bit harder to try to make sure the cow gets completely erased before it gets drawn in the next place. And the CoCo doesn't stop there. You have several options for how to put that rectangular region back onto the screen. What you saw is pset, where it simply pastes those pixels back on. But you have several other options which can do various bit operations on those bytes. To better visualize that, let's take some of the line art that we did from before and try to move the cow across the line art. If we wanted to be more careful about erasing the cow, we can use the fact that the CoCo gives us multiple buffers. So we can have the background stored in an off-screen buffer, and we can use get not only for the cow, but also for the background. we can grab the rectangle of the background that's off screen where the cow used to be, and use that to erase the cow on screen before redrawing it in the new location. On the Apple II, you don't have quite as many choices to move that cow. What you can do is repeat that draw statement where the x-coordinate you start drawing at changes. So in this loop, we'll move it from 20 to 120. As before, the cow leaves a huge trace from where it was. But the Apple does have another trick up its sleeve, the xdraw command. We can keep our loop like before, but rather than doing a draw, we can do an xdraw. And in fact, we're going to do 2 of them. Nifty. No traces whatsoever. But let's take that to the next level. What if we add all of that line art beforehand? Will the cow be able to traverse its path across a colored background without messing up the colored background? It's like a ghost cow. Xdraw does an exclusive OR operation between the bits in your shape definition and the bits on the screen. If either of the 2 bits are 1, XOR gives you 1. But the X in XOR means that if both bits are 1, you get a 0. It's like saying either this or that, but not both. That gives XOR a nifty property when it comes to graphics. Any bit B on the screen, XORed with 0, will do nothing. It will just leave that bit B. So any black that's sitting in your shape definition will do nothing. But any white in that shape definition will reverse the state of the bit on the screen. Because any bit B on the screen XORed with 1 will be the opposite of B. It will flip it. That means no matter what the color is, you will see a change at that location on the screen. And this nifty fact leads to another fact. If you start with a bit B on the screen and exclusive OR it with 1 twice, you'll always come back to that bit B. Because that part gives you the opposite of B, and then this part gives you the opposite of that opposite, bringing you right back to B. That's why in this loop we do 2 xdraws in a row. The first xdraw gives us a chance to see that cow, and the second xdraw will erase it in preparation for drawing it at the next location. If you don't mind going slower, you could add a little pause between drawing and erasing, and that will reduce flicker. Overall, shape tables on the Apple are efficient. You'll notice I did not speed up any of the Apple footage, and the exclusive OR is really nice. While the CoCo gives you a whole bunch of options for bit operations, the most useful one, exclusive OR, is for some reason left off. However, shape tables are a nightmare, unless you also have some extra software that does all of the grunt work for you. Also, shapes on the CoCo give you so many more commands that make it so easy to draw. You don't just have to do 1 pixel at a time. In each step, you can draw whatever length you like in that direction before you move on to the next step. So because of the significant improvement in ease of use, the CoCo wins this round. And now, the final tally! After the first 5 rounds from the first video, we were at a 3-3 tie. But then when it came time for Flipbook animation, CoCo rose into the lead. And when it came time for shapes and motion, CoCo cemented its lead. CoCo wins 5-3. Well, I hope you enjoyed this comparison between the 2 basics. As you may have noticed, some of my judgments were subjective. Fortunately, all of my opinions are correct. Thanks for watching. Let's see what happens as we dive into some of the more advanced graphic... When I was in middle school, I had... Come on. Why do you never see 2 pixels beating each other up? What is wrong with me? And that was today's